Welcome back. Let's talk about engineering materials and manufacturing processes. So there's this video, and in addition to the video, I've posted a PDF file. You can use both of these resources however you want to get the assignment 2 done and see the instructions for assignment 2, which are posted on the website. And basically for assignment 2, I'm asking you to create some notes for these some brief notes for these slides, and then also do some research on a novel or new product, process, material, something like that. Okay, so take a look at the instructions for the assignment, and I'm going to go through these slides faster than I would if we were meeting in person, and just use this as you need to get the assignment done. Okay. So the first thing is there's different kinds of materials, and they have different properties, and we can control these properties by how it's made and what it's made of. Okay, the substance and the process. Okay, so some of the properties of materials, other than just like strength, which is like the kind of the crudest term, to describe a material, is the term strength. There's a lot more properties than strength. There's hardness, there's ductility, or how its resistance to cracking is basically ductility, or cracking or shattering. And there's its ability to be machined, right? Some materials are easy to machine, some not so much. There's wear resistance, fatigue resistance, yield strength. So this is just a brief introduction to materials and the idea that they have different properties. If you study mechanical engineering in particular, you're going to take several, 2, 3, maybe even 4 classes just on materials. You'll spend a lot of time on this kind of stuff. Tensile strength, yield strength. Like I say, this is just a brief introduction. I don't want to get into too much definition of these things, other than to introduce you to the idea that there are different kinds of properties. Okay, so ferrous metals is a broad category of things made of iron. There's lots of iron on the Earth's crust. It's been, science tells us it was collected there by oxidation of iron in the ocean by these little critters that lived, some billions of years ago, and laid down these huge deposits of iron ore in the Earth's crust. So 5% of the Earth's crust. So it's abundant and therefore cheap. But it rusts almost instantly, and it's brittle. So we need to mix it with other elements to form an alloy. So an alloy is just a mixture of several elements. Okay, like iron and carbon is the components of steel. And you can think of it as like frozen Kool-Aid, kind of like Kool-Aid is water and sugar, and then you freeze it. It has certain properties. If you put other things in there and froze it, it would have slightly different properties. So we melt iron and put carbon in it and let it freeze. It's frozen at room temperature, and it'll have certain properties. So there's iron is Fe on the periodic table, and carbon is C. Those are their atomic numbers and atomic weights and stuff you learn in your chemistry class. So most iron alloys contain some carbon. They can also contain other elements. So, for example, cast iron is iron and carbon, and it has 2% or more of carbon. And these are some pictures of some common things that are made out of iron, like a frying pan and a cylinder on an engine, and looks like a little gearbox there. Okay, there's also silicon and in it, which is what you would expect if you were had a very crude process to make this stuff. It would be dirty, so it would have dirt in it, which is silicon, like sand, and it would have carbon because of the fire, right? So you get iron. If you can get the fire hot enough, you can get iron, cast iron. Okay, so the properties of iron are determined in addition to the composition of carbon and iron. They're the process that's used to make these things determines their properties. So you could cool it at a certain rate, and you can heat it up and cool it down again, or we call that heat treating or tempering. And all of those will affect the ductility, the brittleness, the yield strength. Okay, you can change the mixture, like you can mix in, you know, nickel or some other things, chromium or whatever, and get different properties of cast iron. All right. Then you can also control the crystalline structure in large part by the rate of cooling, but also the composition of different elements. You'll get different crystals, and these are some micro photographs of crystalline structure in different kinds of iron alloys. Let's see, so there's also ductile iron, and gray iron and malleable iron, and so once again these all have different chemical compositions as well as processes by which they're made. Let's see, then you get to carbon steel, and this is something with let's see, yeah, if you get less than 2% carbon, which may seem paradoxical actually, that less carbon gives you steel, or maybe it doesn't, I don't know, but anyway, 2% of carbon or less gives you steel versus 2% more of carbon or more gives you iron. And there's other elements that they add to steel to get certain properties, like manganese, silicon, copper, sulfur, cobalt, and nickel superalloys. I put that in bold just because I think they're cool. Okay, so these are different alloys, different chemical compositions for steel. There's something called the SAA classification code, which is a numbering or naming system. I don't expect you to memorize it or anything like that. Just want you to know that something like that exists. Like, for example, SAE 2335 steel is 3.5% nickel and 0.35% carbon. So most people don't have this memorized. You just need to look it up. Okay, here's some forms that steel comes in. This is hot rolled and cold rolled. The shiny one is cold rolled. Comes in plates and bars. All right, you know, cable, tubes, I-beams, wire, things like that. All right. Okay, if you add chromium to steel, you get stainless steel, and 12% seems to be the magic number where it will not corrode at all. In reality, 12% is too expensive, so they put less than that and they let it corrode a little bit. So chromium gives you corrosion resistance and shininess in particular, but it makes it hard to machine. Okay, so, you know, just trade-offs. There's always trade-offs. And here's some pictures of parts that are made with stainless steel. Okay, then so that was ferrous materials, or materials that are based on iron. There's other main materials that we make things out of. So those are materials that are materials that don't have iron as their main ingredient. We call non-ferrous. Aluminum is the largest category. So here's some pictures of aluminum parts. Well, obviously, you all know that aluminum is lightweight, right? That's why we like it. But pure aluminum is super soft, and it's so soft that it's not that useful, and it forms a very hard and non-porous oxide. So we mix it with some other element to make it harder and give it other properties. So some common alloys that we utilize these other elements. So these are this is a list of elements that are mixed with aluminum to make various common aluminum alloys. So the biggest alloying element to aluminum is copper. So, you know, a lot of common parts that are made of aluminum are actually an aluminum copper alloy. Okay, they also add silicon in there and magnesium and manganese. So aluminum itself is very cheap. Copper, not so much. Copper is very expensive. So yeah, so in order to get a useful aluminum alloy, you have to put typically copper in it, and it brings the price up. Anyway, so these are all stronger than pure aluminum. All right, there's some typical parts that are made from aluminum, like a wheel, maybe a bike sprocket, airplane wing, things like that. Okay, that brings us, that was pretty much aluminum. Okay, another non-ferrous metal is copper and copper-based alloys. So there's copper itself, which is characterized by being a good thermal and electrical conductor. So it conducts electricity as well as heat very well. And it's malleable, that is, it can be bent very easily. So that's copper. By itself, it's too soft and too malleable, so we typically alloy it with, you can alloy copper with tin, that gives you bronze, and you can alloy copper with zinc, and that gives you brass. So I think the trumpet is bronze, if I'm not mistaken. Not totally certain on that, but I think so. And those plumbing fixtures there are brass, so those are... So these are, in history, the Bronze Age came first. Well, first there was what? The Stone Age, I guess. Well, there was things before that, but there was the Stone Age, then the Bronze Age, then the Iron Age, right? And bronze melts at a much lower temperature than iron does. So a lot of that was just the ability to make a really hot fire. Okay, so there was probably other factors as well, the availability of the ores and other things, just the randomness of history, right? But anyway, brass and bronze came first, and they're easier to melt, and it could have been that's why they came first. But they're not going to be as hard or as strong as iron alloys. But they're useful because they have good corrosion resistance. They easy to machine. They have other properties that are nice. They have, sometimes you want a little bit of malleability, like in plumbing. You want the things to sort of screw together a little bit easier. So there's other factors. All right. Okay. Then there's nickel-based alloys. So typically, steel is alloyed with nickel, and you get a pretty tough alloy. But if you can use pure nickel, and you can use really high concentrations of nickel in steel, and anyway, in that area, you're starting to get into something called superalloys, and these have super high yield strength and corrosion resistance and heat resistance. So I think that's a roller, which may be used in like food processing, because it doesn't corrode, so you're not going to get rust and stuff in the food. And then the other picture is a turbine blade, which is an extremely high stress environment, high stress, high mechanical stress, as well as high thermal stress. So you need a really tough material for jet engines. So those are nickel superalloys. Then you get into titanium, which is another, it's not iron, it's non-ferrous. Okay, it's characterized by heat resistance, as well as being very strong but very hard to machine. So this picture here is the airplane is the SR-71 Blackbird, which is one of my favorite planes, and flew super fast. It flew so fast that the friction from the air would make it get really hot. So that's why it's built out of titanium. And that's a Cold War plane. The United States spent billions of dollars, over decades fighting communism, and so we used this to spy on the Russians or the Soviet Union at the time. And ironically, we got these titanium from the Soviet Union. The U.S. government set up these shadow companies so they could buy titanium and then funnel that titanium into this secret project that they were doing. So just a little story there. Anyway, they're also used in jet engines, and I think the middle picture here is a bicycle axle. Yeah, which needs to be strong if you're a big guy on a bike. All right, titanium has some other useful properties besides just heat resistance. It has it has the characteristic that your body doesn't reject it, so you can make implants and you know, parts that can be implanted into the human body and they're not rejected, and they don't form clots, so you can make things like heart valves and knee implants and things that, you know, blood clots are bad in the human body. They can cause blockages, and you know, I don't know if that's the same thing as a stroke. I think stroke is when a blood vessel bursts. I'm not sure, but certainly a blood clot can block a blood vessel, which is a pretty bad thing as well. Anyway, it also bonds well to bone, so it's good for making a dental implant. Okay, so, you know, certain properties are, it just depends on what you're trying to get done, and that's why as engineers we study all these different materials, and if you major in mechanical engineering, like I was saying before, you'll take several classes just studying materials, so that you have this body of knowledge that when it comes time to create something new, you can you know, select the appropriate material, or you could realize or discover that none of the existing materials are going to work for what you're trying to do, and that's where the real engineering comes in. You know, you might need to create a new material, a brand new alloy. Most recently that's happening. I just happen to know there's a company called SpaceX, which many of you are familiar with probably. They're building these huge rocket ships out of stainless steel, and they started off with an off-the-shelf stainless steel, and they determined that it would be better if they had some different properties, and so they made their own alloy. I think one of the first new stainless steel alloys to be created in a long time. Anyway, that's titanium. Okay, then there's the class of materials called precious materials, mainly gold, silver, and platinum. Okay, these are tend to be non-reactive. They don't rust, so they stay shiny for a long time. That is, they have good corrosion resistance. They also happen to have good electrical conductivity and good heat reflectance. So that's why you see them on electrical contacts and in certain heat shielding in space. And I think the mask is probably a welding mask or something for heat reflectance. Okay, so that's precious metals. Okay, then there's the whole area of non-metallic materials. Okay, so we just got done talking about metallic materials like iron, aluminum, copper, nickel, and all the alloys that you can make out of those. Well, there's a whole other class of materials made from hydrocarbons, basically, or oil is the feedstock for this stuff. So you can take small little hydrocarbon chemicals, like in this example we're using ethene, and ethene is two carbons with a double bond, and then the hydrogen's hanging off of that. And this is where your chemistry class comes in, is to learn, you know, these elements and the different kinds of bonds. And you take this small ethene and you chain them together, and you basically get a polymer, which we commonly call a plastic, or a polyethene or polythene, I guess. So that's the basic idea of a plastic, or a polymer, really. The term plastic is used for other things, like sometimes we use the term plastic to talk about concrete, but that's a different use of the word plastics. So I guess here I'm really talking about polymers. So there's two categories. There's thermoplastics, and then there's basically non-thermoplastics. So a thermoplastic can be melted and reformed. Here's a good example of several common thermoplastics. There's ABS, or acrylonitrile butadiene styrene. So if you go to Home Depot and ask for ABS, they'll take you to the plumbing section, and there's these black pipes that are used for drains, and they're typically made of ABS. But ABS is used in lots of things. Like here's a picture of a blender and some little meters there. It's very tough plastic, so it's good for, you know, things that are going to take a beating. And then there's acrylics. Acrylics are clear, so if you need something clear, then there's that. There's nylons, which is one of the first polymers that were made. These have very high tensile strength, stronger than steel by weight anyway, but you need a lot of it, you know. It's stronger by weight, but you know, you need a whole lot of it to get the same strength. Anyway, high temperature resistance for a plastic anyway. I think it's somewhere around 350 degrees Fahrenheit that it starts to melt, something like that. Then there's polycarbonate. This is also one of the clearer plastic. Also happens to be a very tough plastic. You can drop it, and it's resistant to cracking. Very high impact resistance. Then there's vinyl, or PVC, polyvinyl chloride. There's a kind of plumbing pipe that's made out of PVC, and windows are common. So that's a common plastic. Okay, then there's another class of plastics called thermosetting, which are plastics that cannot be melted and reformed, right? All the ones we just saw, those could be melted and recycled basically, but thermosetting plastics cannot be. So Alkyds is one kind. So these have a high dielectric strength. That is their good electrical insulator, and they're also very heat resistant. But you can't melt them, you can't recycle them. You know, they're one-time use basically. Then there's epoxies. Once again, these are, once they're formed, they cannot be, you know, broken up and remade into something else. But epoxies are commonly used in something called FRP, or fiberglass reinforced plastic, which is used in surfboards. You know, they take glass cloth and they soak it with this with the plastic itself, the epoxy itself. Or you could take carbon fiber cloth and soak it with the plastic, and then, you know, the difference between FRP and carbon fiber is just the cloth. One is fiberglass and the other one's carbon fiber. So these have certain properties. Among them are they're very light and they're very impact and vibration absorbing. So they're used in some parts of airplanes that don't get very hot. Okay, yeah. So then there's also natural materials. Rubber is one of those. Chemically it's a polymer, but it's a natural occurring polymer, latex, you know, based on latex from a tree, and they cross-link it with these sulfur compounds. We may talk about that in your chemistry class a little bit. I think that's where I learned that. Anyway, don't want to forget natural materials. There's rubber. There's also other kinds of natural materials. There's ones based on plants or cellulosic, you know, wood, straw, grass. Those all have cellulose in them. So flax, cotton, wood. Don't forget sheep's. You know, sheep have wool, and wool is an amazing stuff. You know, keeps you warm, keeps you cool. Doesn't get too wet. It's amazing. Leather, you know, leather's great, you know, for shoes. It's just, it still has some properties that we have not really been able to duplicate for certain things. And stone, don't forget cement. You know, the Romans invented a kind of cement that made a huge civilization possible, and very important. You know, we build buildings. They're all built. They all start with cement on the ground. There's latex rubber. I don't know why mother of pearl is in there. That comes from shells. Well, I guess I'm just trying to make the point that there are things in nature that we still haven't been able to duplicate all their properties, right? Like, people still wear wool because, you know, wool socks, wool caps. You know, mother of pearl has a quality to it of, you know, of beauty as well as other properties that we still haven't really been able to duplicate. Okay, so what we've just talked about is the main materials that historically have been used by engineers to create technology. You know, we talked about ferrous metals, non-ferrous metals, polymers, natural materials. Okay, so as an engineer, you want to learn the main properties of all these things, because if you can use something that's already around and well understood, well, then you're going to use that. So 90% of the stuff you're going to do, maybe more, is going to be well understood engineering materials, both natural and man-made. But you need to understand the properties of those materials and where they may fall short, because you may need to create another material. So that's where the new engineering comes in, is in creating these brand new things. So one of those, an example of that is something called a protein metal matrix. So bone is the natural example for that. Bone in living things is a kind of calcium compound glued together with a protein matrix. So that's a natural occurring protein metal matrix, you could call it. But you can make a man-made one, and I know they've made one with zinc and a protein. I'm not sure how they make it, but it's copying something from nature to make a new material that has new properties that you might need for some particular application where the traditional materials aren't cutting it, that the traditional materials aren't good enough. So another category of these new materials is nanomaterials. So it turns out that when you can control how things are shaped at the very, very small scale, you start getting unique properties. So the picture on the left here is a part of a battery structure that I think it was Altair Nano that was making these batteries. This was some years ago, and they were able to get really high energy densities by controlling the shape of the particles in the battery. And the picture on the right is that could be the skin of a gecko. I'm not sure, but you know, geckos, those little lizards that can stick to the wall, they have this really fine fur on their skin that makes it sticky like that. So the shape and structure of something at the very small scale can give it brand new properties. So in your homework, I want you to look for something like this. I want you to look for a new property, or it could be a new process that's used to make a new material, or it could be a new product that uses a new material, something like that. Okay? Okay, so that was materials. Now we want to talk about how to process different kinds of materials, because it's related to materials. So the traditional way of making things is machining metals. This, you know, from the Iron Age on into the Industrial Revolution and into today, this is how we've made things. We take metal and we machine it. So you could saw it, all right? This is a grinder saw, I think. You can mill it. So a mill is, it's like a drill press kind of, except it moves to the sides, kind of moves up and down and side to side. You can make complex shapes with that. There's a lathe, right? You can turn things around real fast and cut them. You can grind things with something harder than the thing you're cutting, like usually as like iron oxide or silicon carbide, some kind of mineral-based grinding device, grinding wheel or grinding compound or something. Okay, these are used to make complex shapes or to process very hard materials that you can't cut in any other way. Okay, that's grinding. You can sand and polish, which is, you know, related to grinding. You're using a very hard and sharp but microscopic mineral-based cutting compound, and using that to cut off anything that's bumpy, and the result is a very smooth and shiny surface. Okay, you can melt materials and get them to stick together. We call that welding. So the biggest problem with welding is the formation of oxides, because oxide is just rust, right? And rust forms when oxygen in the atmosphere reacts with the base material. That's a chemical reaction, and chemical reactions go faster when they're hot. I think, at least generally speaking, maybe always. I have to ask a chemist about that. But we need to protect the base material from oxidizing when we're welding. So one way to do that is you could use oxygen and acetylene gas. That's gas welding. There the surface is protected by the gas itself, by the combusted gas of the flame, which has no oxygen in it. You can use electric welding, which uses a flux. Whoa! It uses a flux that's on the electrode. You could use wire feed welding with an inert gas like krypton. All of these things are ways to protect the weld itself from oxygen. Okay, that's welding. You can braze. Now braze is different than welding in that there's two different alloys used. So there's the base material, which could be ferrous. It's typically ferrous. And then you've got another brazing compound that you're mixing in there. So you could be using steel and then a copper-based brazing compound, or you could be using copper oh wait, now we're getting into you can braze copper, but typically brazing is like iron and then a copper-based compound. But there's probably variations on that I forget right now. But then there's soldering, which is similar to brazing, except the base compound is, typically it's copper, and then you have a tin-based compound that you're melting into the joint. So there's brazing and there's soldering, and one uses steel and copper, and the other one uses copper and solder. Okay, this is generally speaking. I'm sure there's specialty kinds of processes that maybe for your homework you could go out and find one of those if that's an interest of yours. All right, there's also metal casting. So you can melt metal and pour it into a mold. One way to do that is to make a mold out of sand. So you can press sand together with a binder. In the old days, that binder was oil. Nowadays they use epoxy. So they have sand with an epoxy binder mixed in. You can use plaster. So you can make a mold out of plaster and then pour the metal into that. One way to make the plaster mold is to use lost wax. That is, you build them. This is used in jewelry as well as other things, but you build I forget I don't know what you call it, but like this, let's say you're making a ring, you'd build the original ring in wax, then you could pour plaster around that, and then when you pour the metal into the plaster mold, it just vaporizes the wax. So they call that lost wax process, because the wax original, that's the term, I couldn't remember. The original wax item is destroyed or lost. All right, then that brings us to die casting. Now, if you want to make many, millions of mass-produced parts, you need an automated machine to do that. So a die is a mold that can be automated. So there's pieces that move, robotically or whatever, and you inject the molten material, and then the mold comes apart automatically, and then you can automate that and just repeat that process over and over again. So that's called die casting. So it doesn't work for iron typically, because the temperatures are so hot that the mold would wear out too quickly. But it works for things like aluminum and for plastics, right? For polymers, things that have a low melting temperature are more conducive to making die casting. Okay, another process you can use is forging, which is basically just heating up something and then pounding on it. Okay, think blacksmith. So I think I have a picture of a blacksmith there just pounding on a piece of iron, making, who knows, a horseshoe or a sword or an axe or something. But you can also forge pistons for a car engine. You can forge, you know, tools, wrenches. So when you forge it, you squeeze the grains. You know, there's a grain flow in metals, and you can squeeze those grains into a pattern that can increase the strength, because the stresses in this part will sort of flow along the grain structure there. So yeah, forging can add a certain kind of strength to parts. All right, you can use powder metallurgy. That's where you take a powderized metal and squeeze it together, basically, and then you heat it up a little bit, and just enough to make those little particles melt together a little bit. That's called powder metallurgy. There's different ways to do powder metallurgy. You can look into that more if you want. Let's see. The last thing I want to talk about is 3D printing, or the technical term is stereolithography. Okay, this is building up a part, you know, very slowly from a powder, typically a powder or some kind of resin. You're probably all familiar with this, but there's mineral-based powders, there's metallic-based powders, there's plastic-based powders. There's also now the most popular ones now, I guess, are the extruding, the kind that extrude, you know, melt a thermoplastic. Like PLA is the plastic, I think, that's very common, or ABS is used as well, and they melt it and then extrude it. But there's other techniques as well that are out there. This one here is a powder metallurgy, where you're gluing powder together one layer at a time. And that's the picture in the middle and on the left. The picture on the right is some kind of resin-based technology with a UV light. But in all of these processes, you're building up the part bit by bit, as opposed to cutting off material. So they call this stereolithography. They call it additive manufacturing, because you're taking little, you know, you're adding bits and pieces together to get something bigger. Whereas traditional manufacturing is subtractive, where you're taking a big chunk of metal and cutting off bits until you get what you want. So stereolithography is very important, but you have to keep in mind that it all comes down to the quantity that you're trying to make, because the fastest stereolithography machines are still pretty slow. If you want to make thousands or millions of things, which is what humans do, you need to have automated machinery that does this. And stereolithography is just too slow. You know, you're not going to be able to make thousands and millions of parts. You know, like, let's think of something like those face masks that everybody's wearing now, right? There's 7 billion people in the world. So for this pandemic that's happening, they needed to make, in a few months, they needed to make billions, literally, of masks. So there's just not enough stereolithography machines in the world to do that. So they had to use traditional subtractive methods. So you need to keep that in mind. But if it's a small production run, or something you just want to make for testing, or for you know, part of the product development process, where you're just, you know, handling it in the design office to get an idea of what the final thing is looking like, you know, stereolithography is great for that. Or for hobbyists, or do-it-yourself, you know, kind of custom small production runs. Stereolithography is awesome. It's totally cool. But if you're going to be making lots and lots of something, it's not really very useful yet. And I honestly can't see how it ever will be, because I used to work in factory automation, and we made machines that, just produce hundreds of things. There was one product per second, or several per second sometimes. You'd have products just flying off the end of the machine. Anyway, so that was a lot of material. You've got the slides. You could look at them again. You also have a PDF version of this same material that you're welcome to use. And then there's a document for the actual assignment. So look at the document, the assignment document, and use that to, to tell you what to do, basically. But basically what I'm asking you to do is come up with a short, abbreviated set of notes that sort of summarizes a few points in these slides that we just went through. And then the second part of the assignment is researching on something new, a novel material or a novel process or a novel product. Okay, so read the instructions document. What I'm asking you to do isn't that hard. I think it's a page of notes in various formats. You could use bullets, you could use narration, you could use whatever you want, and then it's some number of words I want you to write about some new thing. All right? So I hope this was helpful to you, and have fun on the assignment. Okay, bye-bye.